the answer turns out to be, maybe not surprising at this point, curvature. Curvature of the surface. The curved surface can be approximated as a collection of individual flat regions. Each region, just like the surface of the Earth, we consider flat. Our building that we took over here had a flat floor, right? We assume that a curved surface, just like a curved line, if you look closely enough, you're going to find that you can approximate it as a straight line if it's small enough. The same thing, any kind of curved surface, if you look closely enough, you're going to find a region where you can consider it flat to the extent that you're able to measure. Now, that might be smaller and smaller and smaller depending on the quality of your measurement and depending on how curved this surface is. But there will be some region, even if it has to be infinitesimal. So you can approximate a curved surface, or describe it as a collection, maybe an infinite collection, of these regions in each of which there is flatness. And that's called local flatness. You have local patches which are flat, but the totality is curved. Now, obviously, if you have a local patch that's flat and another local patch that's flat and another local patch that's flat, there has to be something that tells you how you go from one flat thing like this to another flat thing like that. They can't overlap. You can't extend any one region out far. Once you start extending it out a little bit too far, it's just not describing the surface anymore. You've gone off the surface. So the mathematics of curved surfaces describes exactly this. You have curvature, and it's real curvature, and it can be intrinsically determined, the way that we described before, from within the surface. Even if it was just a two-dimensional space, not the two-dimensional surface of a three-dimensional object, but it was just a two-dimensional space, you could define the curvature, as we mentioned. And locally, small enough regions will give you everything that you require of something that you consider to be flat. You have local flatness. And that's exactly a model of gravity. So we had previously a model of gravity where there was an existence, we needed a space in which geodesics exist, and despite the individual existence of a geodesic and the fact that an individual geodesic could never know that it was in a curved space, there's no distinguishing between the geodesic of a curved space and a non-curved space, right, or a warped space and non-warped space, and nevertheless, neighboring geodesics would deviate. And now we found that curvature did exactly that. Now we find another property of curvature, very much related, which models exactly what we need in gravity. That you have on a curved surface locally flat patches that together the totality exactly models the entirety, where the trick is knowing how to take all these individually flat pieces, because the individually flat pieces don't contain any information about other pieces or how to go and create the entirety, just like the individual geodesics do. But when you put a few together in the right way, then you get the curved surface. And that which describes this curvature is a tensor. Now, at this point, you're not surprised. And it's the Riemann curvature tensor. So the Riemann curvature tensor, which existed for curved surfaces, is exactly the mathematical tool that we need to describe an arbitrary gravitational field. And what will it describe? It describes exactly this property of, on the one hand, individually flat. On the other hand, two individual flat regions don't exactly mesh, and there's a difference between the two due to the curvature, and that's exactly what the curvature measures, which is exactly analogous, similar, and related to two individual geodesics, each of which is exactly the same as if it would be a geodesic of this flat surface. But when you look at the relative behavior of these two geodesics, you find that there is deviation, relative acceleration of the separation vector. And that's exactly what the curvature is. So you won't be surprised to find that the Riemann tensor, which describes mathematically precisely the curvature as it relates to these locally flat patches, is exactly what relates the individual geodesic's deviation. The geodesic deviation is measured by the Riemann curvature tensor.